Last week we looked at discrete probability distributions in general, and now we're going to look at a specific distribution, the binomial distribution. So we'll start with a familiar example, and we have a random variable, which is the number of heads, and we're going to let our coin, we're going to toss the coin 3 times. Let's let it, probability of heads be 0.4, just to make it interesting. And suppose we want to find the probability that x is equal to 2. So the probability we get 2 heads. Well, we can look at a tree diagram to represent the situation. So there are 8 outcomes, and 3 of them result in 2 heads. Okay. Now we can write down our probabilities on the branches here, and we know that these are conditional probabilities. So this is the probability of getting heads on the second, given that we got a heads on the first. Well, we know that these are independent events. So the probability of getting a head on the second is the same as that of getting a head, given that there's a first head on the first. Also, we know that the probability of tails is just going to be 0.6. Find the probability of that outcome. Since, again, they're independent events, we can just multiply the probabilities. So we're going to get 0.4, 0.4, 0.6. So this is the probability of heads, of getting 2 heads, rather, 0.096. So you can see that each of these outcomes is going to have the same 0.4 squared times 0.6 for the 2 heads and the 1 tails. So each of these 3 outcomes is going to have the same probability, 0.4 squared times 0.6. So to get the probability of 2 heads, we simply add these probabilities. So we wind up with 3 times 0.096, or 0.288. We can add them like that because these events are mutually exclusive. So there are 3 ways that you can obtain 2 heads. And this number 3 is just the number of ways to select 2 items from 3. And order is not important. We're just selecting the places here. So there are 3 choose 2 equals 3 ways to select the locations for the 2 heads. Again, 3 choose 2 ways to select where the heads occur, and they're mutually exclusive, so we add 0.96, or it's actually 0.096. Now let's suppose there are n tosses, and we're looking at the possibility of getting 3 heads. Well, here's one possible arrangement, right? So how many ways can 3 heads occur? Well, there are going to be 10 choose 3 possible arrangements of where the 3 heads can occur. So that means whatever this probability is, whatever the probability of getting this is, we will need to multiply it by this number. Well, let's look at the probability of this occurrence. Well, we have 3 heads, 0.4 cubed, right? And then we have 7 tails, right? So the probability of getting a tail is 0.6, right? So that should be our probability, that's the probability that x is equal to 3. We've repeated an identical experiment 10 times. So we had 10 tosses, or trials. They were all identical. The outcomes were independent, right? And for each one, we had 2 possible outcomes. This is called a binomial process. It's a repeated experiment, 2 possible outcomes, and the outcomes are independent. So again, the key features, the trials are independent or identical and independent, and 2 possible outcomes. So we label the probability of a success P, and that's little p, not capital P for probability of an event. So you got to be careful. It could represent anything. It might represent something that doesn't sound like success. And it's important to be clear about what represents success. Here's our general formula for the probability of X successes with N trials and probability of success P. In our last example, we had the N equal to 10. Our X, we're looking for 3 successes. Our P was 0.4. Again, X is 3. And then 1 minus 0.4 is 0.6. And 10 minus 10 minus 3 is 7. In the lab this week, we'll look at finding probabilities using StatCrunch, and we'll look at, as always, more examples. See you in class.